Welcome, my friends. I'm so excited because in this video we get to talk about tree diagrams, which are kind of just a tool that can help you calculate probabilities that would sometimes be difficult to find without them. So let's go ahead and get started. All right, let's start with a somewhat simple example, which is just the tree diagram for flipping a fair coin twice. So the beginning of the tree diagram should just start with a dot. So we're going to start with a dot, and then we're going to have branches off of that dot for each of our events. And our first event would be flipping the coin the first time. So when you flip the coin the first time, there are two possible outcomes. So on flip 1, we could either have H for heads, or we could have T for tails. And I'm going to put a dot on each of those different kind of outcomes. And then from there, we could have the second flip. And on the second flip, we could also either have heads or tails. So all in total, we can really have 4 different outcomes for our 2 flips of the coin. We could have heads, 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 tails, tails, heads, or tails, tails. So we're going to go ahead and list out each of those outcomes. HH, HT, TH, and TT. From there, we can also calculate the probabilities along each of these branches. So along each branch, we say, what is the probability of each of those events? So the chance of flipping heads on the first flip is 0.5. So we put 0.5 along the first branch. Now there's also a 0.5 chance that you flip tails in the first flip. So we're also going to put 0.5 down on the bottom. Now all the branches that come off from one dot should always add up to 1. So 0.5 plus 0.5 does equal 1. Now, since we have an equal chance of flipping heads or coins anywhere, we're going to have 0.5 along all of our branches, which is kind of what makes this a simple example. Then if we want to find the probability of each of the outcomes, we can just multiply the values on the branches. So 0.5 times 0.5 is 0.25. Or 0.5 times 0.5 is 0.25. And it's going to be the same thing along every single branch. So basically what that says is each of these outcomes, 2 heads, heads then tails, tails then heads, or 2 tails, they all have an equal chance of happening, a 1/4 chance, or 0.25 chance of happening. Once you've created your tree diagram and you have all of the outcomes and the probabilities that are associated with them, you can calculate some additional probabilities, such as what is the probability of flipping at least 1 heads? Well, the outcomes HH, HT, and TH all have at least 1 heads. So we can simply add up all of those probabilities. 0.25 plus 0.25 plus 0.25, which is equal to 0.75. There's a 75% chance of flipping at least 1 heads. Let's look at an example that's a little bit more involved than 2 coin flips. Suppose a new test has been developed to detect HIV. Past results have shown that the probability of a positive test is 0.95 when the person has the HIV infection. So a positive test is indicating that someone has HIV. So if someone actually does have HIV, there's basically a 95% chance that this test is going to indicate that. The probability is 0.04 that the test registers positive when the person does not have HIV. So even if this person doesn't have HIV, there's a 4% chance that the test mistakenly says that they do. Assume that in the general population, the probability a person has HIV is 0.02. Now, something to notice here is that in this example, we actually have dependent events. The chance of a positive test depends on if someone has HIV or not. And when you have dependent events, what you're going to want to do when you create the tree diagram is look for the event that is not conditioned upon anything. So what I mean by that is, if we look at this very last probability over here, this is just the general probability that someone has HIV. So that's just the probability of HIV. Whereas the other probabilities are actually going to be conditional. So this one is the chance of a positive test when someone has HIV or conditioned upon someone having HIV. And this is the chance that they have a positive test conditioned upon them not having HIV, right? So these 2 probabilities are conditional, and this one over here is not conditional. If you're creating a tree diagram for dependent events, you're going to want to start with the probability that is not conditioned upon anything. So our first branch is going to relate to HIV. So we are asked to create a tree diagram to model this scenario, letting P represent the individual being HIV positive and H representing the person having HIV. So these are 2 different things, right? So P is just saying, oh, the test says that you have HIV, and H is someone actually has HIV. Since we know this test could give us the incorrect answer. These are not really the same thing, right? And as I mentioned a second ago, we always want to start with the event that is not conditioned upon anything. So our very first branch is going to relate to HIV. So let's start to create the tree diagram. So we're going to start with our first branch, and we're going to either have HIV, which we'll represent by the capital letter H, or they're not going to have HIV, which is just the complement of H. So I'm going to put dots on both of those. We'll fill in the probabilities a little bit later. So that means our other event, which is if they are HIV positive or negative, is going to be our second branch. So in our second branch, we're going to have either positive or negative. We'll let P represent positive, and we'll let P complement represent negative. So there really end up being 4 different outcomes. The person could have HIV, and the test could indicate that they are positive for HIV. They could actually have HIV, and the test could indicate that they are negative. They could not have HIV, and the test could indicate that they are positive for HIV. Or they could not have HIV, and the test could indicate that they are negative for HIV. So the correct decisions would be kind of the ones on the edges here. HIV, and the test says that they have HIV, or they don't have HIV, and the test says that they do not have HIV. The ones in the middle here are going to be sort of mistakes, right? And then the other thing we can do is we can fill in some of the probabilities. Here I have the information again, and it says that the probability a person has HIV is 0.02. So that's going to be the probability along the first branch for HIV. Since all the probabilities coming from one dot have to add up to 1, that means that this probability down here should be 0.98, which makes a lot of sense because this is just the complement of H. So those two have to add up to 1. Next, we can read here, it says that the probability of a positive test is 0.95 when the person has the HIV infection. So if they have HIV, if we're along the first branch here, the chance that they have a positive test is going to be 0.95. So 0.95 must be up here, which means that this must be 0.05. So if there's a 95% chance of having the positive test, there must be a 5% chance of having the negative test in this situation. And then the very last 2 that we can fill in are related to this 4%. The probability is 4% that we have a positive test when they don't have HIV. So this one should be 0.04, which means this one down here has to be 0.96. All right, now the last thing we want to do is calculate all of the final probabilities for these outcomes. So we may want to find the probability that someone both has HIV and is positive. So we would find that by simply multiplying these 2 numbers together, and we would get 0.019. There's about a 1.9% chance that someone both has HIV and is positive for HIV based on the test. And then the chance that they have HIV and test negative is actually going to be 0.02 times 0.05, which is only 0.001, or a 0.1% chance that that happens. The chance they are HIV negative and actually test positive would be 0.98 times 0.04, which is 0.0392. And then finally, the very last one here is the chance that they don't have HIV and they also test negative, which ends up being 0.9408. One more thing you can do to check yourself is make sure all of the final probabilities add up to 1. So these 4 numbers at the very end should also add up to 1 because they represent all the possible outcomes for kind of the scope of all of these events together, right? So if you add up these 4, they should also add up to 1. So at this point, we have calculated quite a few different probabilities, and it's important to understand exactly what each of those probabilities are. So I've written out the probability statement for every single one of the numbers here. And I want you to, think about this and have this in your head. Actually, what have we calculated? What actually are all these numbers? So here they are, and I've kind of color-coded them based on what type of probability they are. The first one we have is the very first branch. And remember, I told you before we even made this tree diagram is the very first branch should relate to a probability that's not conditioned upon anything. So this is just the general probability that someone has HIV, or the general probability that someone does not have HIV. So that's P of H and P of H complement for that 0.02 and 0.98. And then I said the second branch relates to conditional probabilities, right? These are the probabilities of either a positive or negative test, given that someone either has HIV or does not have HIV. So this is the probability of P given H, the very first one of 0.95, P complement given H is the 0.05, P given H complement is 0.04, and P complement given H complement is the 0.96. So these are all conditional probabilities. And then finally, we have the final outcomes, which are H and P complement, H complement and H complement and P complement, which are all of the ones over here. So we have found quite a few different probabilities, but these are not all of the probabilities. Which ones are we missing here? Well, we don't have the probability of P or the probability of P complement just on their own, right? So that's something that was not given from the tree diagram. We only have just H and H complement. And we also don't have the other conditionals, like the conditionals with H first, H given P or H given P complement, right? So the tree diagram doesn't necessarily give you everything, but once you have calculated all of these things, you can actually go out and calculate a couple of those other things, which is what we're going to look at now. All right, so we're going to go ahead and answer a number of these different questions here. So I'm going to kind of go back and forth between my Word document, which has those probabilities that I wrote down, and also between the screenshot, which has the tree diagram. So the first question says, what is the probability someone has a positive test? So that's just the probability of P. So what you might want to do is, I would encourage you, once you've created your tree diagram, to write down all the probability statements associated with, all those numbers that you found. And none of those numbers are the probability of just P by itself. So we can't really go to any of those values there. So we're going to have to go back to the tree diagram and see if we can figure out how to find the probability of just P by itself. And this is a little bit tricky, and maybe I wouldn't expect you to, get this on your own. But this is a common question that I'm going to ask, so I'm going to expect that you're able to get the probability, the general probability of whatever is on that second branch, right? Right now, all we have is those as conditionals, right? We have P's as conditionals, but what's the general probability of P? And here's the way to think about it. Well, if you think about the probability of P, the probability of a positive test, there's two ways you can have a positive test. You could either have a positive test with HIV, or you could have a positive test without HIV, right? So really, the way to find the probability of having a positive test is find all the times when you could have a positive test and add those probabilities together. And those two outcomes are going to be having a positive test with HIV and having a positive test without HIV. So you can simply just add up those two AND probabilities, 0.019 and 0.0392, and those are the only two times you could possibly have a positive test. So if you add those two together, you're going to get the chance of a positive test. So that's what I've done right here. The probability of a positive test is the probability of having a positive test with HIV, that's the 0.019, plus the probability of a positive test without HIV, and that's the 0.0392. So when you add those together, you get 0.0582. There's a 5.82% chance that someone has a positive test. And you could also find the chance of a negative test by taking 1 minus this if you wanted to, but we were only asked for the chance of a positive test. Next, we are asked, what is the probability of a false negative? They have HIV and the test is negative. Well, that's just asking for the probability of H and P complement, right? That they have HIV and the test is negative. The test is negative is positive complement. And in this case, you don't really have to do any work if you've created your tree diagram and you understand, all the values, right? Because the chance of H and P complement, that's one of the outcomes. H and P complement is 0.001. So that's all we have to do. We just have to find that number on our tree and write the number down. Some of these questions are going to be right from the tree, and a few of the other ones, like the first one here, you might have to do some calculations. The next one says, what is the probability of a false positive? They don't have HIV and the test is positive. So that would be they don't have HIV, H complement, and the test is positive. So then we would look back at our tree here, H complement and P. Here's H complement and P. Well, it's another one that we have on the tree. It's 0.0392. All right, two more. What is the probability someone has a negative test given they have HIV? So the given there is the key here. This is going to be a conditional probability. And the one that they're asking for here is the chance that they have a negative test, that's P complement, given they have HIV. Remember, the one that's given or conditioned upon must be listed second. So remember that some of the conditional probabilities are given on the tree and some are not. So is this one of the ones that was given on the tree? Well, this is where it's going to be helpful to look at kind of the list of all the probabilities here. They asked for P complement given H. Well, P complement given H, P complement given H is one of the ones that we have here. So our answer is just going to simply be 0.05. Remember back on the tree again, this is asking P complement, actually it's right here, P complement given H is this probability right here, 0.05. And finally, the last question, what is the probability someone has HIV given that they have a positive test? So once again, we have another conditional, but this one is actually kind of a switched one, right? The chance that someone has HIV given that they have a positive test. So if we look back at our, our sheet here that has all the probabilities written down, we don't have any of the probabilities that are conditional with H first, right? All of our conditionals have P first, because if we look back at the tree, the first branch related to H, so they're all going to be given some form of H. So we don't actually have this probability directly from our tree diagram. So how can we find this? Well, you're going to have to use the formula. So the formula for conditional probabilities is change the given sign to an and that's going to be your numerator. So instead of H given P, we have H and P, and then you divide by the second outcome, which in this case is P, the probability of P. And then you see if you have all of those numbers, and indeed we do. H and P would be right from the tree, right? H and P is 0.019, and the probability of P is what we found in the very first question. So we can simply divide those two numbers, and we will get 0.3265. There's about a 32.65% chance that someone has HIV given that they have a positive test, which might seem alarmingly low to you, right? Like the chance that someone actually has HIV if they have a positive test is only like a 33% chance. And that is actually kind of a problem sometimes with some of these tests, that you might think that they're going to be very accurate because they say 95% of the time when you have the test, we're going to indicate that you have the test. But really, when you kind of get into some of these probabilities, some of them can be a little bit surprising, right? The chance that you actually have HIV given you have a positive test, only 32.65%. So you might want to get a second test just to make sure. All right, so here is a question for you to try. It says, if someone is lying, assume that there is a 78% chance that a polygraph test, which is a lie detector test, will correctly identify them as lying. If someone is telling the truth, assume there is a 7% chance that the lie detector test will falsely accuse them of lying. Someone answers 80% of a long run of questions truthfully. So create a tree diagram and let P represent that the polygraph is indicating a lie, and let L represent that the individual is lying. For your first branch of the tree diagram, you should be identifying which of these events is not conditional upon anything, and that should be your first branch, and then the other numbers are going to relate to something that is conditional. So take a few minutes to see if you can create this tree diagram. If you get stuck, I'm going to show you the tree diagram in a second, and then we're going to also answer some questions. But make sure you pause the video and you give this a shot first. All right, let's see how you did. So the probability that is not conditional upon anything is, once again, this last little part here. Someone answers 80% of a long run of questions truthfully. So whether or not the individual is lying or not is going to be our first event that we need to put on our tree diagram, because this is not conditioned upon anything. It's just in general what percent of the questions they're answering truthfully. So that means our first branch is going to relate to either lying, they're actually lying, or they're lying complement. And so we're going to have the two dots there. So this would be telling the truth, really, and this would be lying. And that means that our other event, which relates to what the polygraph indicates, is going to be our second one. So now P is going to represent the polygraph indicates a lie, or P complement would be the polygraph indicates that they are telling the truth. And then we can list out all our outcomes. We could have they could actually be lying, and the polygraph indicates they're lying, so it kind of catches them lying. That would be L and P. They're actually lying, and the polygraph indicates they're telling the truth. So this is like they got away with it. And then we have they are telling the truth, but the polygraph indicates that they are actually lying. So that would be incorrect as well. And then we have the final correct decision, which would be they're telling the truth, and the polygraph indicates that they are telling the truth. And then we can go ahead and we can put the probabilities on the branches. So if we kind of glanced at some of those numbers again, 80% are answered truthfully. So lie complement is truthfully. So that means we actually have 20% chance of lying and an 80% chance of telling the truth, right? And then they say there's a 70% chance that the polygraph test will correctly identify them lying. That says that if they are actually lying, the chance that it catches them. So that's going to be the 78% here, which means we have 22% here. The chance that they, the polygraph indicates that they're telling the truth when they're lying. And then we have the final one here, which says if someone's telling the truth, there's a 7% chance they're going to falsely accuse them of lying. So if they're telling the truth, that's down here. The chance that it falsely accuses them of lying, that would be here. That's going to be our 7%, which means we have a 93% down here. And then we can fill in all of the, the final probabilities here by simply multiplying all these together. The chance that they're lying and the polygraph indicates they're lying is a 15.6% chance. The chance that they're lying and the polygraph indicates they're telling the truth is 4.4%. And then we have the chance that they are telling the truth, the polygraph indicates they're lying is 5.6%. And the chance they're telling the truth, the polygraph indicates they're telling the truth is 74.4%. So your next task before we move to the next part here is to write down all the probability statements associated with all these numbers. So with the first branch, with the all the ones in the second branch, and all the final probabilities. So take a second to see if you can get that done. All right, so here is the result that I got. The first two probabilities are just the general probabilities of L and L complement at 0.2 and 0.8. And then all the other ones here on this, the second branch are all the conditionals. They're either P or P complement given L or given L complement. So we have those four here. And then finally we have the AND probabilities, L and P complement, L complement and P, and L complement and P complement. So I've just copied down all of those numbers. So hopefully you got that correct. All right, so then we have another question here which says, based on the tree diagram on the previous slide, answer the following questions. So there's a number of different questions here. So give all those a shot, and then I will be answering a few of them. But I still want you to try these out before you see me get the answers. So give that a chance right now. All right, I'm back, and I've spaced things out a little bit so that I can fit all of the answers. So the first problem says, what's the probability the polygraph indicates that an individual is lying? So if you look at all of your outcomes, again, this is asking for the probability that the polygraph indicates something is lying. That's P, right? So that's just the probability of P. And if you look at all of your outcomes here, you don't have that one, right? So you're going to have to look back at the tree diagram, which is right here. And remember the way that we did this last time, right? There are two different ways that P could happen. P could happen, basically the polygraph could indicate someone's lying when they're actually lying, or also when they are not lying. So use the same kind of procedure as last time to figure that out. You're going to have to end up adding up two different numbers. If you don't remember, go back and watch that part of the video from earlier, because I'm not going to solve this one right here. This is the challenge one, or the one that needs to be submitted. So the next one says, what's the probability the polygraph will correctly indicate an answer as a lie? And be very careful to kind of parse the language here, right? So correctly identify an answer as a lie. This is not a conditional. This is just saying in general an answer. So that's like out of everything. What's the chance that it correctly identifies an answer as a lie? Well, that means it has to be a lie, and the polygraph has to indicate it is a lie, right? And that is one of the ones that we had from before, P of L and P. That's this one right here, which is 0.156. And we also had that one, I believe, on the tree diagram at the top, right? L and P was the probability was 0.156. So that's the chance that the polygraph will correctly indicate an answer, a general answer, as a lie. The next question says, what is the probability that the polygraph will wrongly indicate an answer as a lie? Well, that means that the person actually has to be telling the truth, so that's L complement, and the polygraph has to indicate that it thinks that you are lying, and that would be P. So altogether we have L complement and P, which once again is one of the numbers that we had from our probability statements. L complement and P is right here. It is 0.056. So the chance that the polygraph will wrongly indicate an answer as a lie, well, there's a 0.056 chance of that happening. What's the probability the polygraph will indicate the individual is telling the truth given they are actually lying? So this is going to be a conditional, given that they are lying. So that's given L, and they're asking for the probability of P complement, the probability that the polygraph is indicating that they're telling the truth, right? So is this one of the ones that we have written down? So let's take a look. Probability of P complement given L, yes it is. It is right here, so the answer should just be 0.22. Finally, what's the probability the individual is lying given the polygraph indicates that they are lying? Well, that's the chance that they are lying, that's L, given that the polygraph indicates that they are lying, which is P, right? So this is not one of the ones that we have on our list of probabilities here. We only have the ones with the L's as the conditioned event, right? We don't have the ones with the L's listed first. So that means we're going to have to use the formula. So change the given to an and. So instead of L given P, it'll be L and P. And the denominator will be the event that was given. Now, I'm not going to solve this right here because to find the probability of P, you'd have to actually solve the very first answer here, which was the one that I left blank here. So this is another one left for you to complete. If you've completed the very first question, then you should be able to complete this one as well. All you'd have to do is take L and P, which is 0.156, and divide by your answer from the very first part. And I think that is all I had to talk about here related to tree diagrams. So hopefully you found that useful, and I will see you in the next video.